Hi guys, today I would like to introduce new concept electrostatic potential and capacitance. So in previous chapter we learned about electric forces and electric field. The aim of physics is to make things easier. So in last chapter we learned about electric fields and electric forces. They are somewhat tedious because we always need to more care about directions. But we will define same concept with further in detail with much more simpler than the earlier. So for that we need to introduce a new concept which is known as electrostatic potential. So let's recall for this. I need to recall some earlier definitions what we learned in mechanics and all. So first the definition of work and energy. The work and energy they both are related and we learn about work energy theorem also. So let's define work. The work is defined as the product of force times displacement F dot S. The dot product of force and displacement we define as work. The work units are joules. Here I need one more definition which is known as potential energy. The potential energy is defined as the ability to do work by virtue of its position or condition. So if an object is placed at a height due to because of its position, the object gains energy, so that we known as potential energy. So we need to interrelate work and potential energy. So let me recall that first. If you remember this statement, which is change in potential energy is equal to work. So to understand that, take a case. Suppose initially I am having the stone at here at point A, you can take. So this stone is at a height from the ground h1. Now the stone is kept at here by applying a force now which is at the point B. If I take that position at here, so this is the position at a height from the ground. If I can take, this is height h2 from the ground. Now if you can write the difference in height from A to B, so this is the difference in height, so that I can write h2 minus h1. Now to displace this stone from here to there, it means I applied force. So force applied by me along this direction. And we know that the gravity will be acts force always in the downward direction. Now to prove change in potential energy which is equal to work. So at the point B, if I write what is the potential energy at here, mgh2, and at point A, what is the potential energy? It is mgh1. So according to definition, change in potential energy, it means mgh2 so change in potential energy which equal to mgh2 minus mgh1. You can take it out mg common, mg of h2 minus h1. So mg, so the difference in height, if I can call that as h, the difference in height. So in the diagram I will mention h2 minus h1 which equal to h. Now if I can write this mg as nothing but force, so since F equal to ma, in the place of a I can write F equal to mg, and h, the h is nothing but the displacement from here to there. So this is the displacement s. So in the place of h I can write that displacement. The force done displacement we called as work. So this is the proof that change in potential energy, so change in potential energy which equal to work. So change in potential energy which equal to work. So whatever work I did in this case, so that work is stored at point B in the form of the potential energy. That's the meaning of that. Okay, if we do work, so that work stores in that object at that position. It only happens due to because of this g, or acceleration due to gravity. So here g is acceleration due to gravity, is a gravitational force. So this gravitational force is a conservative force. So in only conservative forces, so this takes place. It means if I do work against conservative forces, so my work will be stored in that object in the form of the potential energy. So let's see in detail what are the conservative forces. So we already know about some conservative forces. So conservative force is nothing but a force which gives back work that has been done against it. So here in this case, the work done to keep the object on top of a hill, so that is the work done by me. So the same work is given back once the ball starts to roll. When the ball starts to roll, so whatever the potential energy is again converted into kinetic energy. So here the conversion is only takes place because the gravitational force is a conservative force. A part of the gravitational force, we are having some other conservative forces. So the elastic potential energy, the energy stored in a spring, that is also comes under the conservative force. It means if I compress a spring, so I am doing work, so my work will be stored in the spring in the form of elastic potential energy. And the gravity, we just learned about the gravity. If you do work against gravity, so here I want to keep an object against the gravity, so I need to do work. So whatever the work we did at here, that will be stored in the form of the potential energy. Now a part of the gravitational force and elastic force, so our electrostatic force is also conservative in nature. So if electrostatic force is conservative in nature, what is the advantage? So whatever we do work, that will be stored in the form of the potential energy. And not only that, the concept of the potential energy comes into picture or takes place in only conservative forces. If the electrostatic force is not a conservative forces, we do not talk anything about the electrostatic potential energy. So this potential energy concept comes only if the force is a conservative force, and that is the advantage here. If the force is a conservative forces, so whatever we do work against it, so that work will be stored in the form of the potential energy. Now, once we started to talk about the energy, so our concepts will becomes easier because energy is a scalar. It's very easy to deal with the scalars because we can simply add them just like numbers. But once comes to electric field, electric forces and all, so those are the vectors. So the work is little tedious. We need to much concentrate about the directions. I thought you might be face troubles while doing the problems. So those concepts are the little tough than these concepts. So finally, so I can give the conservative forces example. The spring force and the gravity and electrostatic force are the examples for conservative forces. Again, I am repeating, if the force is conservative, what is the advantage set here? If the force is conservative, then we can able to talk about potential energy. So when we can talk about the potential energy, so there is an interchange of the energy and work. So that gives much more knowledge about the electrostatic energy further. And one more very important point in the conservative force, that is the conservative force is path independent force. What does it mean? Suppose if you are moving an object from down to top in the given picture, if you can choose two paths, one is a green path, another one is a blue path. Even though if you choose any path, so the energy at that point is mgh. It means the conservative forces do not depend on the path what we have chosen. It's only depend on initial and final positions. It do not depend on the path. So you can bring the object any crooked manner, any curve like that. So it's do not depend on the path what we have chosen. It's only depend on the initial and the final positions. So this is a very important point when you are learning about conservative forces. Now comes to sign conventions. Since potential energy depends upon work and work formula contains force and displacement. Now here we can see the green arrow mark shows the gravitational force or electric force, and the red arrow mark shows it here the external force. It means work done by us or work done by me. I am applying a force, and the D is the displacement direction. Now in the first point, if you can see, if the external force is doing work against gravity, that the point you can keep in mind. Understand the arrow marks carefully. If the external force is doing work against the gravity, so by the time the work will be increases, because whatever I am doing the work, so that work will be stored in the system. So we can say that work as positive. Now you can see the second point. Now here there is no external force. Gravity itself is doing the work. If object is kept at here and if I release the object is falling. It means gravity is doing the work. Now the force direction and the gravity is the direction. Now the object is falling. It means object is losing its energy. So the potential energy of the object is decreases. But if you can take the first case, so I am lifting the object from the down to top. So I am lifting the object from the down to top. It means I am doing the work against the gravity. So I am doing the work. So my work is stored in this object in the form of the potential energy. So that work we call as positive work. So the positive work, negative work done by the external force or work done by the field. So these are the energies which can give positive work or the negative work. So in a simple point, if you can remember, if the external force is doing the work against the field, so now that work is positive. Now if the conservative force is doing work, by the times you can take that work is a negative work or the potential energy goes to decreases. Okay, so these are the sign conventions we need to follow, especially we are dealing with the work and potential energy conversion. Now let's talk the same case at here, sign for work and energy. If the work is positive, it means if an applied force is in the same direction of displacement. Now the applied force direction and displacement direction, they both are the same. The work is positive, but the force mg, that does the negative work. Yeah, because I am doing the work against the gravity, so obviously it forces negative. Now if you can see this another example, suppose you want to keep an object at a height h, a position from A to B against gravity. Now in this case the gravity is acting downward direction and you want to do the work against gravity. So now you are keeping object from A to B. Now the object at point B having potential energy, that is mgh. Now at level B the potential energy U is mgh, it's a positive work. Now the external force here means I myself take out the object and kept at point B, means I did positive work which against gravity. Now if I did positive work, what the gravity does? It does negative work because it's a conservative force. The external force F against gravitational field increases the potential energy, and if once you release, the field gives back the work. Since the gravitational force is a conservative force, whatever I do work, so that work will be stored in the form of the potential energy. Now let's apply some same concept to our electrostatic concepts. Now this is the uniform electric field. We already know uniform electric field due to a positive charge, or the uniform electric field due to a two oppositely charged parallel plates. Okay, now here our conservative force has changed. So here what is the conservative force? Here the electric force is a conservative force. Strictly electrostatic force is a conservative force. Now in this electric field, if I bring a charge and I'll keep at a location in the vicinity of this field, it means suppose you are having a positive source charge, understand the picture, and far away you are having positive test charge. One is a source charge, the big one is a source charge, and small one is a test charge. Now since the both are the positive, what happens? They both starts to repel each other. That's its nature. Suppose I am forcefully holding the positive charge object, I am bringing close to the source charge. If you can see, what is my force direction? I am holding, I am bringing. It means I am doing work against the electrostatic force of the source charge. Now you can compare that mechanics works and here electrostatic works. Now, to talk about the potential energy, our first condition should be conservative force. Yeah, here the electrostatic force is a conservative force. Yeah, that condition is satisfied. And the next, in the potential energy, whatever work we do, that work will be stored in the form of the potential energy in that charge at that particular location. Now, here in the second figure, the charge at that particular location is having electrical potential energy. How did it get that energy? It got that energy because I am doing work. I am holding the charge. I am bringing from one point to another point. It means I am doing work against the electric field. So my work will be stored in the form of the potential energy. Now the charge at that location having electrical potential energy. Now if you can change the location, automatically the potential energy also will be changes. Consider, suppose if plus q is a source charge and if I can keep at here, I am having a small test charge. So this is my positive test charge. So which is a positive, which is located at here. So this is at a distance r, sorry, so that is at a distance from the source charge at a distance r2. So let this point r2, let the point B. Now I applied a force on this test charge and I displaced from there to at here within the electric field at a point A. So this is the point A. So this point A is at a distance r1 from the source charge. So this is the location of the r1. Now to keep a source charge from point B to point A, I applied a force. So this is the force applied by me. Okay, so if to calculate that, so what is the work I did? The work done by me equal to the force applied by me times, let me take here the small displacement dr. So I did a small work. To calculate the total work, so the total work done by me equal to integral of dw of me, which equal to integral of the force applied by me times the displacement from at here r2 to r1. Now here I don't know how much I applied force, but here you can see the force applied by me which exactly equal and opposite the force applied by the electric field. Yeah, because of this is the positive charge small q, here the source charge capital Q, obviously there is a force of repulsion. So this is the helpful case at here. I don't know how much I force applied because I kept the charge in my pocket and I started to walk in the electric field. But what is the force applied by me? That force is exactly equals and in the opposite. Now to calculate my work at here, work done by me, which equal to, in the place of force applied by me, I can substitute R2 to R1. So that is the force of electric field, which is a negative, times dr. Now we know what is the force exists between them. So that is the Coulomb force. So integral R2 to R1 Coulomb force, K times Q upon R square times dr with the negative sign. Now if you can do the integration, the total work done by me, which equal to, so here the constant terms are K minus Q are the constant, integral R2 to R1 1 over R square dr. If you can do the integration for 1 over R square equal to minus K capital Q upon, so that is integral 1 over R square equal to, so R power minus 2 integral dr. So that you can apply integral x power n formula. So that is x power n plus 1 by n plus 1. So that is the integral x power n dx. Now here you can get r power minus 2 plus 1 by minus 2 plus 1, which equal to minus 1 over r. So in the place of that, I can write a small integration minus 1 over r to the limits r2 and r1. Now if you can substitute limits, work done by me equal to minus times minus it becomes plus. So K capital Q small q upon 1 over r1 minus 1 over r2. So if you can write that, so work done by me equal to K q small q upon by r1 minus K q small q upon by r2. So this I can write as it is the potential energy at point A minus potential energy at point B. So we can write the potential energy formula at a given point. So as per the definition, so the charge in the electric field, so if this is the charge, so it is located in this electric field. So because of that charge present in that electric field in that location, so there is potential energy exist. Now at the point B also potential energy is present, at the point A also potential energy is existing. Now we got a definition that the change in potential energy, so the change in potential energy is equal to work done by me. So here my work is the positive because I did work against the field. So here my work is positive which I did against the field. Now if you can write what is the work done by the electric field. The electric field also does the work which is exactly opposite to me. So that is negative of work done by me. So which equal to negative of UA minus UB, which you can write that the work done by the electric field in terms of UB minus UA. So the work done to bring a charge from one point to another point within the electric field. Within the electric field is defined as potential difference. So here UA minus UB we define as electric potential difference. So that we define as electric potential difference. Suppose, think about like that. If I am bringing this charge not from point B, I am bringing that charge from infinity. I am bringing that charge from infinity, not from the point B, because I need to select a point which is known as a origin, or where the force is equal to 0. So to take the force is equal to 0, or a reference point, that is the correct word I shall use it here, to make a reference point where the force is 0, that is obviously at infinity. Suppose if I am doing work to bring a charge from infinity to a point in the electric field. So in that case, so in my integral at here, so which I solved at here, now so that will be changes as, so if you can rewrite that, the work done by me equal to k q small q by r1 minus k q small q by r2. If r2 equal to infinity, that is the starting point which I have taken, now this term will becomes 0, because 1 over infinity that will becomes, so 1 over infinity that will becomes 0. The second term will become 0. So we can define as the work done by me equal to k q small q by r1. So this is the convenient definition to define potential energy. So now here I can define potential energy. Potential energy, strictly electrostatic potential energy at a point in an electric field is defined as work done to bring a test charge from infinity to at a point in an electric field is defined as electrostatic potential energy at that point. So according to definition of electrostatic potential energy, the work done to bring a test charge means positive test charge, from infinity to at a point in an electric field is defined as electrostatic potential energy at that point. So we learned that if a charge is located in the electric field, so this charge will contribute potential energy. So let me take the diagram for a moment so that I can easy to understand. If it is a positive source charge, you take any point in this location, in this vicinity, either here or here or here, anywhere, either 1, 2, 3, or if you can take 4, any point, any location. According to definition, each position having its potential energy. We will write the potential energy formula at that point. So it is a k capital Q small q by the distance r. So that is the potential energy formula. So how we define this potential energy? So to define potential energy, I need to do the work done by me. It means I need to bring a positive test charge from infinity to at a point in the electric field. So I carried a positive charge in my pocket. I'm coming all the way from infinity, walking and coming, and I stayed a location at point 1 within the electric field. Now to bring that test charge from infinity, I did work. So whatever work I did, that work is stored in the form of the potential energy at that location. So that defines the electrostatic potential energy. So see the definition again. Electrostatic potential energy at a point in an electric field is defined as work done to bring a test charge from infinity to a point in an electric field is defined as electrostatic potential energy at that point. So in this session, you just understand the difference between the potential difference. So this is the potential difference and electrostatic potential difference, and one more definition that's known as electrostatic potential energy. So these are the very basic points to understand this chapter.